In question 7, the resistance of 1 meter length of a resistance wire is 7.6 ohm. A length of this wire is taped on a meter rule. A crocodile clip is connected to one end of this resistance wire exactly at 0 mark. On the figure 7.1 shows the crocodile clips connected between the terminal P, connected to terminal P. The second terminal Q is connected to a movable contact. So we can change this position. Basically, what happens if we change this movable contact? Originally it is placed here, but we can change its position, and with respect to its position, the reading will change as the length will change. A second terminal Q is connected to a movable contact using a long length of a connecting wire. A movable contact is in contact with the resistance of a wire at length L from 0 mark to the ruler. The movable contact is placed at different points on the resistance wire. The resistance R and length of a wire depends on L. On a figure 7.2, sketch a graph to show how the resistance vary with length for the values of L0 and 1 meter, and mark appropriate values for the axis of on the graph. So as we know, resistance and length are directly proportional to each other. When two quantities are directly proportional, there should be a straight line which is passing through origin. But we have to label the axis as well. So first thing, the graph should be a straight line, and then you can clearly see in the question they mentioned that if the wire is having a length of 1 meter, it is having a resistance of 7.6. So if this length was 1 meter, and I have to label them, so if I say label this as 10, this will be 5, so this will look like 7.5 or 7.6, and this one is 1 meter, this will be half meter. So when resistance and length are directly proportional, when two quantities are directly proportional, there should be a straight line which is starting or passing through origin. Figure 7.3 shows a battery of electromotive force EMF. In this part A, as we know, we want to sketch a graph for resistance and length. And we know resistance and length are directly proportional to each other. So if resistance and length are directly proportional to each other, so there should be a straight line which is passing through origin. And then you have to label the axis. How you label the axis? So you can clearly see that they mention when the wire is having a length of 1 meter, it is having a resistance of 7.6. So if I label the axis, you can first label the axis and then sketch or draw a line. That is also right. Like if you label the axis, this is 0.1, 0.5, and this one is 1, and here we have 5 and 10. So when the length is 1 meter, the resistance is 7.6. So between 5 and 10, there will be 7.5. So a bit more than that, 7.6. And join. So that shows relation that they are directly proportional, and when the length is 1 meter, the resistance is equals to 7.6. The next part, figure 7.3, shows a battery of electromotive force EMF 12 volt, which is connected across the whole 1 meter resistance wire. So basically what happened, the total 12 volt is across this one, but the part which we are using in our experiment, that will have proportion of it, and resistance and length are directly proportional, and resistance and voltage are also directly proportional to each other. State what is meant by the term electromotive force. The term EMF or electromotive force means it is work done on unit charge when chemical energy changes to electrical energy. So that's a standard definition for electromotive force or EMF. And EMF 12 volt means that 12 joules is transferred to 1 coulomb charge so that it can move in the circuit. The current in resistance wire. So how we can find the current in the resistance wire? We have the formula V is equals to IR. So voltage is 12 and the resistance 7.6. So when you use the formula voltage divided by resistance, it will be 1.6 amps or ampere. The potential between the terminal P and Q for the length 0.35. Resistance and voltage are directly proportional and resistance and length are directly proportional. So you can it's a 1 mark, so even you don't have to use a formula, you can use a simple ratio. The ratio between length and voltage, if the 1 meter length was there, how much voltage it was having? 12 volts. So if we have 0.35 meter length, what will be the voltage? It will be X. So you can cross multiply. So it will come out as 4.2 volts. The charge that passes through a resistance in 5.5 minutes. Whenever you are using a time should always be in seconds. So you have to convert these 5.5 minutes into second. So current is charge divided by time, or charge is current multiplied by time. Current is I and time small t we normally use because capital T is normally for time period. So when you multiply, it will be 528 coulombs. Figure 8.1 shows a ray of a red light incident one side of a glass prism in air. For the red light, the refractive index is NR. The angle of incidence is 53 and angle of refraction is 30. Calculate the refractive index. Yes, Hashim, what you're saying? Which part you're talking? Question 7, part A2. Sorry, Hamza. Yes, Hamza.
Sir, in question 7, part B22. Yeah, this one.
Part B, this one. This is part B2.
Yeah.
2, yeah.
2.
The potential.
Yeah, I used L equals 0.35, and then previously they said when length is 1 meter, the resistance is 7.6. So I used ratio of resistance, and then I used ratio of voltage to resistance. Why was it wrong? It was wrong. The answer came wrong. The marking scheme was different. Like, is it a correct way or?
No, that's the same way, because if I'm taking basically the ratio of the resistance, the ratio of the voltage, and the ratio of the length all will be same. Means like L divided by L1 will be equal to R divided by R1 will be equal to V divided by V1. Means the total voltage divided by. You should get the same answer. Maybe mathematical, or you're maybe in substitution you are doing some mistake. Otherwise, you should get the same answer. It does not make difference. If you took first the ratio of the length and resistance, and then you took a ratio of resistance and voltage, your answer should be correct. I will check after the session. I will check your submission, and I will point out what mistake you are doing.
Okay,
But the math, it
thanks.
should give you the right answer. Method is correct. Figure 8.1 shows a ray of a red light incident. So we need a refractive index. Refractive index is sin I over sin R. Angle of incidence is 53 and angle of refraction is 30. So it will be 1.6. On a figure 8.1, sketch a line, indicate the path of a red light when it emerge out, and why the quantity. Okay, use a screen annotation to complete the path of a red light. So it will bend away from the normal as it is traveling from glass to air. The next part, why the refractive index, the simple question is why the refractive index is not having a unit. Explain why a quantity refractive index does not have a unit. Because it's a ratio, and whenever anything is a ratio, the unit cancel out. That's why it does not have a unit, because it's a ratio. Compared to air, how much it is having the ability to bend light. For a violet light, the refractive index is NV. A glass is slightly larger. For a glass, it's slightly larger than NR. Because the refractive index is a ratio of the two quantities, that's also right. Identical quantities. So on the figure, sketch a line to indicate the path of a violet light in the prism and when it emerge out. And then when a ray of a, so complete the path of the violet. The red one is already done. This was the red light. Use the screen annotation to complete the path for the violet. Because violet is having a higher refractive index, so it will bend more, greater change in speed. Then the next part, when a ray of a light incident on a prism dispersion produce a continuous spectrum of color light. State how the speed of a light in glass depend on its frequency and how this is shown by dispersion of white light in a prism. So basically how the speed of the light depends on the frequency. Higher frequency means there will be a greater change in the speed. So if it is having a higher frequency, speed decreases more. So violet is having less speed and it diffract more. So larger frequency result in small speed. And then this is a statement. And then you will compare that the violet is having the higher uh, less speed because it is having a higher frequency. Look, basically why the frequency remain remain constant and the speed and the wavelength are variable, because frequency is a ratio between speed and wavelength. So the ratio remains same, that's why the frequency does not change. Yeah, F is not changing, but the thing is, when you're comparing in the beginning, when you have a white light is a combination of violet, indigo, blue, green, yellow, orange, and red. Violet from the beginning is having a high frequency, and red from the beginning it is having a short frequency from the beginning. And when they travel from one medium to another, their speed changes. As the speed of a violet changes, so violet bends the more and the red bends the least. So to have a higher frequency, if there should be a greater change in speed. Then this is the last question. The chemical symbol of element lithium, which is Li, the proton number of lithium is 3. Figure 9.1 is representation of the nucleus of a radioactive isotope, lithium, that is about to decay. Write down using a nuclide notation the symbol that represents this isotope of lithium. You can use a screen annotation to write answer for this part. For lithium nuclide notation, and it's an isotope of the lithium. You can use any space on the screen to complete this. As you can see, there are 3 protons and there are 5 neutrons. So that's why nucleon number is 8 and the proton number is 3. The isotope of a lithium decay by beta emission. When it's emit out beta, first what happened in a beta emission, a neutron, one of the neutron breaks into proton and electron. So proton number will increase and the nucleon number will, the proton number will increase and the neutron number will decrease, but the nucleon number will remain unchanged. So use the same representation as figure 9.1 in a space after the arrow and draw a diagram of the nucleus. So basically the shaded one is representing a proton. So what happened to the proton number? The proton number will become 4. And the nucleon number, the neutron number will be 4 as well. It was 5 in the beginning, but now it is 4. And the shaded one is a proton. So 4 protons and 4 neutrons will be there. And what we have, write a name of the particle that is identical as beta in the space provided. So what we have electron in this side. A radiation detector is set up in the lab where there is no radioactive sample. On 6 separate occasions, the detector switched on for 1 minute and the background counts are there 23, 27, 25, 24, 20. Suggests why the readings are not identical. Why sometimes we are getting small number of the count, sometimes we are getting higher count number. Because radioactivity is a random process. Like sometime you might have more radiation, sometime you will have less radiation. So these emissions are from not from source, these are from surrounding, and the radioactivity is a random process. Or radioactive emission is a random process. Even though we have a source from background radiation, they are like detection from the background, still they are random, sometime more, sometime less. Suggest a possible source of this background radiation. Why there is a background radiation? What could be the possible source? Maybe uh, cosmic rays, radiation from atmosphere, maybe nearby nuclear power station is there, nuclear waste is there, a radon is also a radioactive, rocks, buildings, soil, earth, they also have some radioactive material. A sample contain only one radioactive isotope is brought into a lab. The half-life of the isotope is 15 hours. So means approximately after 15 hours, it will change half of its original value. The sample is placed near to a radiation detector in this lab. The detector is switched on after 1 minute and it recorded. Hussein, I will answer your question how the radioactive uh, how radiation destroy a DNA in the nucleus. Just this is the last part I'll solve and I'll answer your question. The sample is placed near to a radiation detector in this lab. The detector is switched on and after 1 minute, the count 440. So detector is recording 440 counts. But keep in mind, because this is a continuation of the question, so already they discuss about the background. So when they discuss about the background, you have to include the background radiation as well. So your detector record 440 counts, but which include background as well. So what is the average background here? What will be the average background? Average of these numbers 23, 27, 25, 24, 20, 25. Add them and divide by 6. It is 24. So average is 24. So even though they did not mention in the question, but like in this part, but you have to include in your calculation whenever a background radiation is given. So the detector reading is equals to source plus the background. Source reading, source detector is recording 440. The background radiation are 24. So how many are there from the source? So it means the source will record 440 minus 24, which will be equal to 416. So these are the radiation from the source. And after half-life, after 15 hours, only the source radiation will become half. The background radiation will more or less on average will remain 24. So we want to find how much sample, what will the detector reading after 45 hours, means after 45 hours means after 3 half-lives. So after first half-life, the source radiation will be 208, half of this. Then after another half-life, it will be 104. And after another half-life, it will be 52. Because after 15 hours 208, after another 15 hours 104, after another 15 hours 52. But the detector is not only recording source, it is recording source plus background. So after 45 hours the source radiation are 52 and the background radiation are 24. So the detector reading will be 76. Is it clear? So this was the last question related to this paper 4. Then how these radiations, your question was how these radiations are harmful, how they can cause a mutation or destroy the DNA. Basically, these radiation, alpha particle, which are two proton, two neutron, beta particle, which is a fast moving electron, and gamma, which is energy, what they have a property which we call ionization. So the term ionization means breaking down the molecule, breaking down the structure into ions. So breaking down of the nucleus, breaking down of the atom or molecule into ions, that is called ionization. So because these radiation, when a human body or a person is exposed to these radiation, they can cause ionization, they can remove the electron out from the atom. That's how they cause a mutation or destroy the DNA, which leads to development of the cancer. They can be used for treatment of the cancer, these radiation, or it can also be, if a person is exposed, healthy cells are exposed uh, to these radioactive radiation, it can develop or cause a cancer. In nuclear fuel, uranium, the particle, uranium is a radioactive normally, because we cannot directly say it is emitting out alpha, beta or gamma. It's a radioactive, so it can emit any of them. It can emit alpha, beta, gamma, any of them, but majority radiations are in a beta range. And uranium fuel, when we use a uranium, what we do, we take a heavy nucleus uranium and we target this by a fast moving, by a neutron, which causes splitting into lighter nuclei and release three more neutrons, and these neutrons collide with further more uranium nuclei and multiply this reaction. That's why we call fission reaction is a chain reaction, like it multiply one, release three neutron, then three further multiplied, and so on. In a nuclear fission, when we target the uranium by a neutron, it emit out neutrons, and these neutrons further collide with another neutron and cause a decomposition or breakdown. How much time does it take for a person? That depends on how long a person is exposed to radiation, what is the intensity of the radiation, and what is the source which is emitting out radiation. So it's not like a fixed rule, like a person exposed for 2 minutes